This is what I'm calling Duple. It's a physical model of a Paul trap, or a quadrupole ion trap, a device which traps charged particles in a flapping electric field. In this series, I'm going to take you through my build process for a project like this. For any design project, I like to break things down into phases. The typical flow is concept, followed by prototyping, followed by production. These phases get broken down into actionable tasks once we start a phase. Often, we don't know enough about the later phases to start nailing down the details of implementation until we really start making things. So, first step is concept development, which is essentially what does it do and how do people interact with it. I'll link to the research paper and the original video that inspired this video by Action Lab. The goal of the Duple is to simulate the trapping phenomenon that occurs on charged particles in a Paul trap field. In the Paul trap, 4 electrical potentials, 2 positive and 2 negative, are arranged at the corners of a square. The magnetic potential this creates can be represented by a series of arrows showing the direction of push or pull a particle experiences. A particle placed near one of the positive poles is pushed to the center. A particle placed near the center is pulled off of the center by the negative poles. This vector field is what we want to represent mechanically instead of electrically. One question that arises is why not use all positive poles? This would appear to fully trap the particle by always pushing it towards the center. The answer to this is literally Nobel Prize winning, and a bit beyond the scope of this video. The short answer is, by introducing a negative component and flipping between the polarities, a stable system can be achieved. This flipping of the polarities can be indicated by the vector field flipping directions. Since we're really only interested in the center of the graph, we can remove the electromagnetic poles and only keep the vector field. Since we are attempting to represent this field with a rigid physical part, we can also pause the switching action and examine just a snapshot of the vector field. We've got one direction that pulls the ball towards the center and another that pushes it off a hill. Each of these forces is strong near the poles, but weakens near the center. Let's hold on to that thought for a moment. Now, we're going to dive into the math here, but don't be scared. Math is often taught in classrooms with a focus on computing answers. Out in the real world, math is simply a tool used to describe the world. We're trying to describe a dynamic electrical potential with physical parts. Math just happens to be the most convenient and accurate way to do this. If we take a slice of this potential surface and start experimenting with the math, we can get a visual understanding of how it's going to behave. A constant number gives us just a horizontal line, which doesn't really push the ball in any particular direction. Tilting the line does get the ball to roll downhill, but the slope stays constant. We want a curve that gets weaker as we approach the center. Quadratic functions are some of the simplest curves found in nature. Plotting x squared, we can see it satisfies the requirements. It gets stronger as you get further away from the center. Inverting the equation and switching to the y-axis gives us negative y squared, which satisfies the opposite requirement. Plotting these equations separately in 3D gives us 2 orthogonal parabolas. Blending them together by adding them gives us the surface we are after, which can be stated as z equals x squared minus y squared. This surface is called a hyperbolic paraboloid, or a saddle curve. The math is just a model of real-world phenomena. It's a way to describe how things already work. To describe the saddle curve shown here, I could call it a Pringle, and a decent number of people would understand the reference, but we wouldn't be able to do anything with that information. I can type in z equals x squared minus y squared into a computer and plot the resulting surface. I can't really type Pringle shape into a computer and expect a surface. So we have a surface that roughly simulates the behavior we want. Half of it attracts the particle to the middle, the other half repels the particle from the middle. In the Paul trap, these forces are balanced by cycling the poles. This is often visualized as the surface we've been working with flapping between a high and low potential. The paper goes into more detail on the supporting math, but the core concept is that if we spin the surface we've generated, we can approximate the forces generated by the flapping field with a rigid surface. We can visualize this by plotting a line where the flapping surface intersects with an arbitrary plane. Now I'll hide the surface, but keep the curve going. This represents a slice of the forces a particle would experience. Now I'll introduce the rotating field. We can see the curve and the rotating surface actually track very nicely, which is exactly what we want. This means we can approximate the complex flapping of the Paul trap by simply spinning a static shape. The next question that comes up is how fast should it spin? If the saddle spins too slowly, the ball will fall off because the force that attracts the ball to the center won't come around fast enough to act on the ball. But at the other end of the spectrum, if it spins too quickly, it's likely to throw balls across the room. So there's probably a happy medium. Now onto the initial bill of materials, and what is actually needed to make it. Turning this into a physical item that we can make, we're going to need some material for the parabolic surface, a particle, electronics to spin the device at a specific speed, and a method to detect the ball being picked up. I really like the look of walnut and brass, so I plan on using that for the parabola and other visual parts. For the particle, I'm going to start with a hollow brass ball. For the electronics, I plan on using a small microcontroller to manage all the inputs and outputs, a photoresistor to detect if the ball has been picked up, and a small stepper motor to spin the saddle. To drive the motor, I know I'm going to need a stepper motor driver, and I plan on kind of powering this whole thing with USB-C. At this point in a project, I like to do some quick 3D rendering to understand what the final object is going to look like. So once we know roughly what the components are going to be, we can start playing with them in space. I know I want to machine this on my Pocket NC, so that caps the size of the parabola to about 4 inches by 4 inches. The stepper is pretty large, so I'll probably want to tuck that in under the parabola. Other than that, I know I would like a ball storage position when the device is off. This will set the general shape of the finished product. Bringing this into CAD, I can start playing around with how I want to integrate the walnut. Reviewing the design I settled on, brass being laminated in between some layers of walnut horizontally, I really like the pattern that emerges on the surface with brass. The first step in working with electronics is to create a block diagram to understand the programming flow, and an electrical schematic to understand the electrical components. This is typically followed by a breadboard prototype to combine the two, allowing for a quick assessment of basic functionality before committing time to a more formalized design. Translating all of this into physical parts, I need a small through-hole light-dependent resistor, a thin NEMA 17 stepper motor, a TMC 2208 stepper driver, an AT-Tiny 85 microprocessor, a USB-C power sync device, and a voltage converter. Breadboard starts by connecting all of the components together. Power comes in from the USB-C and is routed to the 12-volt rail and the buck converter. The buck converter converts 12 volts down to 5 volts for the microprocessor. The processor is connected to the board and supplied with power. The stepper driver is connected to both power rails, the stepper, as well as the processor. And finally, the photoresistor is connected to the processor, which monitors its output. Making all of these connections on a breadboard gives us a first look at the functional circuit and the amount of space that is needed. To make this pile of electrics do anything, though, the microcontroller needs some code to actually perform the tasks required. So, onto the code, the ones and zeros that do stuff. The goal of the code is to transform our block diagram into instructions a microprocessor can follow. We'll start by rewriting the steps sequentially, and then slowly add detail in subsequent passes. First, we'll want to tell the processor what's plugged into it. So, there's a light sensor, and there's a stepper motor driver. Everything else is not directly connected to the processor, so it has no way of communicating with it. Next in the flowchart is the question, has the ball been picked up? We've decided to detect this using the light sensor. If the ball is blocking the light, it's in place. If it's missing, we can assume it's been picked up. So, translating that into code, basically we look at the light sensor, and if the light sensor is above a certain value, spin the motor. If it is below that value, stop the motor. This style of pseudocode is a helpful method of problem solving at a high level. If your code doesn't make sense in plain English, it's going to be difficult to translate that into working code. The next step is to take this plain English description and translate it into code. Programming and syntax are a bit beyond the scope of this video, but it's relatively easy to translate this into usable code. I'm going to use the common library XL stepper to assist in spinning the motor smoothly. I'll initialize a few variables to hold the LDR values, as well as calculate the velocity ramp of the stepper. Because of how the Excel stepper library works, I need to slowly increase the speed until it's at the desired max speed. I do this with a combination of while and if statements. That's pretty much all of our code. Uploading this to the breadboard prototype, we can see the code reacts as expected. At this point, we're ready to start designing a circuit board, but since the circuit needs to fit into the overall assembly, we're going to jump into the CAD model first to see how much room we have for the eventual PCB. It's notoriously difficult to walk through a CAD design process in a compelling way on video. I'm going to walk you through my initial thought process followed by the final CAD model. Just know the process of going from initial thought to ready to manufacture design is full of dead ends, false starts, and a lot of really rough sketches. So, the first step in creating something in CAD is to establish scale. This can be determined by the manufacturing capabilities, user interface, existing components, or just made up on the spot. For this project, I want to be able to manufacture the curved surface on my Pocket NC. That makes 4-inch diameter the largest I can go. This lines up pretty well with the scale I had in my head, so I'm just going to start with that. Looking at the breadboard, I'm confident all the selected components will fit in the preliminary design at the scale I've chosen. Since all of the electrical parts can and should be stationary in this design, I can put them in the base and have the saddle be its own rotating thing. I modeled the saddle curve into a cylinder, then had to do some CAD shenanigans to get the brass inserts to show up properly, but the overall form is pretty simple. I essentially just wanted the rotating assembly to have a ball next to it, and I just connected that with a nice round over piece here. But go into the model now. Actually going to slice it. It's easier to see the components. So up top is all wood and brass. This will be custom CNC machined, and that'll be kind of, for the next video, the details on how I'm going to make that. But moving downward, we've got the first 3D printed part. So this part here is a saddle adapter. And this is what I'm going to use, just 3D printed. It's what I'm going to use to connect the saddle to the NEMA 17. I have the majority of the functional parts made out of 3D prints. This allows me to have the precision and tweakability of a 3D printed part with the aesthetic of the wood and walnut I ultimately want. Whenever I can, I try to separate things that are likely to change from things that take a long time to make. I would hate to have created a beautiful curved surface only to have to remake it from scratch to tweak how the bearing fits together. Flexibility and taking advantage of the strengths of your manufacturing process are hallmarks of a well thought out design. The saddle curve interface, as well as the inner housing, which holds the circuit board, stepper, motor, bearing, and screws, everything together, is 3D printed for this reason. If I need to tweak something in the future, it's an easy 3D print instead of redoing all the hard work with wood and more exotic materials. The circuit board is just a stand-in at the moment. The outline is made up. I'll do my best to fit all the parts I need onto the board. If I'm wrong, I'll have to come back to the CAD and update it to give myself more room. The stepper motor will be directly screwed to the circuit board, which simplifies the assembly. The outermost surface is a piece of matching walnut to hide all the functional components, and at the bottom I add some feet and a base plate to make it look just a little bit nicer. This project is open source, so I'll leave a link to the source files in the description for those that are interested in literally how I put the model together. If you're interested in more of a how-to video, leave me a comment. If enough people are interested, I can make that a tangential series. Finally, putting it all together. I believe the design is ready to manufacture, but there's a great opportunity to test the design as is to ensure there are no tweaks I want to make before committing significant time and effort to the final build. 3D printing is fantastic for this. More than half of the parts are already 3D printed, but there's no reason I can't 3D print all of them to test that they fit together and that they function as intended. 3D printers are priceless for just this alone. The alternative is to make the whole thing with real and expensive parts and just kind of hope it works. Putting this prototype together is not meant to look good, but purely test if everything works as intended. The electronic guts are hanging out the side, none of the materials are correct, and it doesn't look very good. The important part is that it works as expected though. If anything is wrong at this stage, it's better to catch it here and fix it before the expensive materials are pulled out. The first step is to prepare the raw materials. The inside is going to be mostly 3D printed. I'm going to outsource the circuit board to a vendor, and the main base will be made from a piece of walnut. The saddle is really the only piece that needs custom material prep. I need to laminate some brass between several pieces of walnut. I chose to do this with Dupal epoxy. It's important to scuff up the brass before applying the epoxy to assist with adhesion. Getting all these pieces together was pretty stressful. The epoxy I chose has a 5-minute cure time, which means I needed to move quickly. Once the epoxy is in place, it's important to apply a lot of clamping force to ensure a good bond. To machine this saddle, the plan was to use one of my CNC machines, the Pocket NC. Any CNC machine needs to hold onto the material blank while removing material from it. This is called work holding, and it's a significant part of the time invested in CNC machining. If you can't hold on to something, you can't machine it. For this specific piece, I chose to mill a pocket and insert a few threaded inserts into the wood. This would allow me to bolt everything together using a custom plate and shaft and mount it securely into the Pocket NC. Making the shaft and the custom mounting plate went perfectly. Absolutely nothing went wrong at all. To carve the main pocket, I chose to use a simpler CNC than the Pocket NC. It's called a Shaper Origin, and it's essentially an aimbot for a hand router. I can feed it an SVG file and use that to cut out my desired shape. This only works for simpler shapes, but I designed the base to be very simplistic for this reason. To get a CNC machine to make parts, a program describing how the machine should move to generate the shape is needed. This process is called CAM, or computer-aided manufacturing. It's basically a set of instructions the CNC machine will use to remove the material where I want it to. The finished G-code of this piece ended up being roughly 500,000 lines of code, all of which is available on the project's GitHub. Pocket NC has a really cool online simulator you can plug this into and see how the machine moves to create this geometry. Once all the prep work and CAM is done, the machining essentially becomes babysitting some machines. The Pocket NC took about 8 hours to machine this piece. This is due to the work holding not being very rigid. Since I'm holding onto only wood, but machining brass in the wood, I have to take fairly conservative cuts. Unfortunately, during the machining process, a tragedy struck, and I lost some steps in one of the axes. This sent the end mill straight into the workpiece, carving a big hole in the almost done piece. I ended up filling it in with brass dowels off camera. I'm going to choose to see it as a beauty mark instead of a defect. Also, I don't want to have to start over from scratch because I was pretty much almost done. The base took only about 20 minutes, but the 20 minutes were a lot more active. I need to stand there and move the router around by hand, which is perfect for podcasts. Once the machining is done on the Pocket NC, I can file and sand the part smooth and apply some oil. I've done this dozens of times, but it's always satisfying to watch a coat of wax getting applied. It entirely transforms the piece. Once I received the circuit board and components, I realized I had screwed up big time. I ended up picking very small components. They were an absolute pain to see, let alone assemble. If I had to do this whole part over again, I would pick a larger package size for almost everything just to make assembly easier. Just for reference, here's the size of a quarter, here's the size of a grain of rice, and here's the size of a resistor. Lesson learned. Once all the components are finished, it's time to put the parts together. Throughout the process, there were small tweaks and little changes that get made before the final assembly occurs. Often these are one-off tweaks, and it's kind of easier to do them by hand in the moment than it is to go back to CAD and reprint the entire thing. Once it's all together, though, there's nothing quite like seeing the idea come to life for the first time. Thanks for joining me on this journey. It was a lot of fun taking you all through my process. All of these files are open source and freely available on my website and GitHub, so don't forget to like, comment, share, and subscribe. It really helps get the word out. Gotta please the algorithm and all that. See you in the next one. Bye.